Let's continue our talk today. We talked last time about, we finished our talk about the diesel cycle. We have represented the cycle that can be applied for early version of diesel engine, in which, as we said, the injection just occur at the top dead center, and all the combustion process just take place during the expansion stroke. This is the early version of the compression ignition engine. We inject the fuel once the piston reaches the top dead center. So in this case, once the fuel is injected, combustion start. It will try to raise the pressure, but the piston is moving down, so it will equalize the pressure at the beginning of the expansion stroke. So the combustion process in this case will take place at constant pressure. But if we inject the fuel a little bit earlier, before the top dead center, almost it's about from 10 up to 15 degrees before the top dead center. So in this case, the combustion part of it will take place at constant volume, like the case of gasoline engine, and the remaining part will take place at constant pressure. And in this case, the cycle for the modern compression ignition engine, we call it actually the dual cycle, or what we call the limited pressure cycle. We call it the limited pressure cycle or the dual cycle in this case. Still, this cycle also, even for the dual cycle, still it is air standard cycle. In this case, we don't consider also we have intake or exhaust valve. We consider actually we don't have fuel. The system is totally closed, and we just, instead of combustion, just we add heat, and also instead of exhaust stroke, in this case we reject heat to the atmosphere. In comparison to the actual cycle we have intake valve, in which we have intake charge, which is air plus fuel in case of gasoline engine, and in this case we are talking about diesel engine, so the charge should be air. It will be compressed, and at the end of the compression stroke for the dual cycle, the injection start about 15 degrees before the top dead center. Then part of the combustion process should take place at almost constant volume, and the remaining part should take place at constant pressure at the beginning of the expansion stroke. And at the end, we should have the expansion stroke. And finally, we should have the exhaust stroke. We should have the exhaust valve is opened, and then we can have the exhaust gases leaving. So the system in this case, for the actual engine is an open system. It is not a closed system, in which we have fuel plus air. Here in the air standard dual cycle, as we said, only we have air, and we assume the system is closed. We don't have combustion in this case, but we have part of heat is added at constant volume, and the remaining part of heat is added during the expansion stroke at constant pressure. And then we should have the expansion stroke, and at the end we should have the heat rejection stroke. I will not be repeating all of the steps here, like what we have done for the auto and also for the diesel cycle, but let's write down here some main processes for the limited pressure cycle or the dual cycle. So the air standard dual cycle, or we call it actually the limited pressure cycle. Okay. If you look at those processes on the cycle, also representation on the pressure volume diagram. If this line is representing the top dead center, the volume inside the cylinder when the piston is at the top dead center is represented by the clearance volume. And if this line represents the volume at the bottom dead center, from bottom dead center to the top dead center, this volume we call it the displacement volume or the stroke volume in this case. If we start the cycle here, as we used to do from the beginning of the compression stroke, let's say this is point 1. Still the standard is, the cycle is air standard cycle, so we consider the compression process from the bottom dead center to the top dead center as isentropic compression. And in this case, that should be the compression work, and this work is a negative work because it is applied on the piston. The power is coming from the crankshaft during the compression stroke, and then it moves the piston. So we have negative work in this case applied on the piston, which is the compression work. Usually we have in the dual cycle, if we are talking about the actual diesel engine, we have the injection here, the injection of the fuel. The start is almost 15 degrees before the top dead center. Once we start to inject the fuel, the piston will be reaching the top dead center, and the combustion almost takes place when the piston approaches the top dead center. Part of the combustion process, as you know, in case of diesel engine, the diesel fuel just needs some time to reach the self-ignition. So it takes more time for combustion. That's why here we have part of the combustion will take place actually from the process from 2 to 3. So we have heat added here. And the remaining part of the combustion fuel will continue the combustion process from state 3 up to state 4. So here also we have another heat added under constant pressure. So part of the heat is added under constant volume, and the remaining part is added under constant pressure during the expansion stroke. Then we continue the process of expansion from point 4 up to point 5. We will have in this case the expansion work, which is a positive work generated by the piston due to the combustion process. Once the exhaust valve here شباب at point 5, the exhaust valve will be opening at point 5. At point 5 here شباب, the pressure inside the cylinder is little bit higher than the atmospheric pressure. So once we open the exhaust valve, so the exhaust gases will be just throttled in the opening of the exhaust valve and will be leaving. That will result in some heat to be rejected in this case from sudden heat rejection at constant volume when the piston is at the bottom dead center due to the charge of the exhaust gases leaving the engine due to the pressure difference, not due to the piston movement. So we should have heat is rejected here from point 5 up to point 1. This is the dual cycle. If we are talking about the engine, then in this case we should have the exhaust stroke, the piston will be moving back almost, we can say, under constant pressure from one, let's say, to any point here, let's say to prime, and then the process will be reversed back, which will be the intake stroke. After the exhaust stroke, we are finished with this cycle, then the piston will be reversing the motion initial to point 1 to have the intake stroke. But here, as we said, we are talking here about air standard cycle. We are not talking about intake or exhaust stroke because we don't have actually any valve. Just we assume in this case, as we said this for the other two cycles, that the system is closed. Just we add heat and reject heat. So the cycle will be just limited to the point 1, point 2, 3, 4, and point 5 in this case. Is that clear, Shabab? Is it clear?
Yes.
We say the area under the PV diagram for a closed system, as we said, the system is closed, so work is equal to integration of BdV. So that work should be represented, the network of the cycle should be represented by the area contained on the PV diagram. So that should represent the network out of the cycle. And if we represent this cycle also, we can represent it on the TS diagram, the temperature entropy diagram, process from 1 to 2, which is the isentropic compression, from 2 to 3, this is the constant volume heat addition, and then from 3 to 4, this is still we have heat addition, but under constant pressure. Then we have from 4 to 5, this is the process of the expansion, in which we have the expansion work. 1 to 2 we have the compression, then we should have from 5 to 1, this is the process actually of the heat rejection. But by definition of the entropy, we said Q is equal to TdS, or we can say actually on the temperature entropy diagram, on the TS diagram, the area contained by the cycle here should be representing the net heat transfer. Okay, and we say that for a cycle, if we have a system working on a cycle to generate continuous power, Q net is the same as work net. Okay, Q added minus Q rejected should equal to the work out, which is the expansion work, which is a positive work, minus the work input, which is a compression work in this case. I will leave it for you to just go for this cycle as we did for the diesel and the auto cycle. You can go step by step. That will be, inshallah, a homework assignment, and then you can go and prove the relation for the thermal efficiency of the dual cycle or the limited pressure cycle. In this case, if we consider, if we apply the first law of thermodynamics, Q minus work is equal to delta U for the process of heat addition 2, 3 up to point number 4. In this case, we can apply for constant volume heat addition. The heat added in this case will equal to CV multiplied by T3 minus T2, like what we did in the auto cycle. But we have another part for the heat addition under constant pressure. In case of constant pressure, we should have boundary work, which is equal to pressure multiplied by delta V. Pressure multiplied by delta V, we can combine it with delta U, it will be delta H. And delta H will equal to CV delta V. So it will be CV multiplied by T4 minus T3. And this is the heat added, the net heat added to the cycle. Part at constant volume, and the other part is under constant pressure. Type, this is the heat added, and also we have the heat rejected. Heat is rejected for process from 5 to 1, which is constant volume. Constant volume, following the ideal gas model, it will equal to delta U, which will equal to CV multiplied by T5 minus TU. Okay, and we have the definition of the thermal efficiency is work net divided by Q added, or we can divide by mass, so it will be specific work divided by the specific heat. And then it is the same as Q net. Work net is the same as Q net divided by Q added. Q net is Q added minus Q rejected, as we used to, it will be 1 minus Q rejected divided by Q added. If you substitute here, we have Q added and the Q rejected, then we can get that should equal to 1 minus Q added, Q rejected, which is CV multiplied by T5 minus T1. Q added is CV T3 minus T2 plus CV multiplied by T4 minus T3. Okay. Yeah, you can take this relation and then you can develop a relation for the thermal efficiency as function, first of all, of the compression ratio, which is the ratio of the volume V1 over V2. Also, we can get this thermal efficiency dimensionless in terms also of the cutoff ratio, which is the ratio of the volume after the combustion process to the volume before the combustion process, for the process in which we have the heat added under constant pressure, which is equal to V4 divided by V3. Like what we have done, this is for the diesel cycle, like what we have done last time. Also, we can get another parameter, we call it the pressure ratio, which is the ratio of the pressure after the combustion to the pressure before the combustion for the heat added under constant volume. So RB is the pressure ratio V3 divided by V2. Just to take all of this dimensionless parameter definition and then try to go through this definition of the thermal efficiency and try to get the thermal efficiency as function of those parameters. Dimensionless parameter, function of compression ratio R, which is V1 over V2, function of the cutoff ratio, V4 over V3, function of the pressure ratio, which is B3 over V2. Like what we have done last time, the temperature relation, you can just do it, and that should be an assignment for you. If you did this, you can just look here. You can obtain this expression for the thermal efficiency of the dual cycle. It will be 1 minus 1 over R to the power K minus 1. Without the term between the bracket here, that should be the Otto cycle. Okay? But here with the term between bracket here, that is actually the representation of the dual cycle. If we have the compression ratio, the cutoff ratio is equal to 1, that means 0.4 is the same as 0.3. And also we have the pressure ratio, RB is equal to 1. So in this case, this will be the special case that we will head back to the Otto cycle. So if we have the pressure ratio is 1, if we have the cutoff ratio is equal to 1, then we'll get back the definition of the Otto cycle. That means the efficiency of the dual cycle will equal to the efficiency of the Otto cycle if we have the cutoff ratio is equal to 1 and the pressure ratio is equal to 1. But if you look at this term, between the bracket, this term is greater than 1 because the pressure ratio B3 over B2, B3 is greater than B2. So the pressure ratio should be greater than 1. The cutoff ratio V4 over V3, V4 is greater than V3. That means the cutoff ratio is greater than 1. And the specific heat ratio K is greater than 1. That means the all term between the bracket will be greater than 1. And at the end, if we have the same compression ratio, that means the Otto cycle will be the limiting efficiency in this case. It should be higher than the diesel cycle, the dual cycle, and also higher than the diesel cycle, as we said last time. So in case, if we have an engine, gasoline engine and diesel engine, if they are working at the same compression ratio, Same compression ratio, the gasoline engine will be able to generate high pressure and high temperature in this case, and it will result in higher thermal efficiency. Okay? But otherwise, the efficiency of the diesel engine should be less than the efficiency of the gasoline engine in this case. Also, we can just take this term, the definition of the heat added. That will be also another assignment, and then you can get the cutoff ratio as function of the pressure ratio and also function of the compression ratio R. If we define this as Q added, let's consider the total value. So we can say Q added will equal to MCV T3 minus T2 plus MCV T4 minus T3. Just take T1 as common and then T3 over T1 and here T4 over T3. And just to go with this process like what we have done last time. So based on this relationship, we can get the cutoff ratio, get a relation as function of the compression ratio R and the pressure ratio RB. Then we can substitute in the thermal efficiency and we can get this thermal efficiency as function of those parameters R and RB. Just we can exclude in this case the cutoff ratio. Okay? So we can get the thermal efficiency as function of the compression ratio. And then we can compare all of the cycle. Now we have already developed this term for the thermal efficiency as function of the compression ratio for the case of Otto cycle. And we have developed this also for the case of diesel cycle. And now we have developed it for the dual cycle. So that we can compare the three cycles if we have the same compression ratio. Okay? So if we have the same compression ratio, as we said last time, for the diesel cycle, in this case, if you look at the definition of the thermal efficiency, even for the dual cycle here, this term between bracket will be greater than 1. That means for the same compression ratio, the efficiency of the Otto cycle will be higher in this case. But this is the only situation that we can have the efficiency of a gasoline engine working on Otto cycle is greater than the efficiency of a diesel engine when we have the same compression ratio. But as you know, diesel engine and gasoline engine does not intersect with the operating compression ratio. Usually gasoline engine are limited by knocking, so they cannot go above compression ratio equal to 11. But in case of diesel engine, we cannot actually work at compression ratio less than 15, and that has to be higher in this case. And that's why the diesel engine at any other condition should result in a better efficiency. But as we said, why we are using almost a gasoline engine in different application, because gasoline engine results in less emissions, and also the gasoline engine can run at higher speed. In case of diesel engine, as you can see, the combustion is delayed. It takes some time. Part of it take place at constant volume, and the other part take place at constant pressure. So it needs time. That's why we cannot actually go for a diesel engine with higher RPM. And also the diesel fuel is a heavy fuel, and it results in additional emission in terms of soot and also particulate matters. And also due to the higher compression ratio, usually the diesel engine is a noisy engine, and it is heavy engine in this case. But it is efficient. As we said, in all cases, it is efficient engine in this case. Here also, the efficiency is the definition of the indicate mean effective pressure. We have went through this last time also, which is the network indicated mean effective pressure, which is the network produced by the cycle divided by the displacement volume. And we can express this dimensionless also, so that we can compare also the three cycles based on the dimensionless parameter. So the indicated mean effective pressure, which is the network divided by the displacement volume, which is V1 minus V2. That is the displacement volume. Okay. Working it based on the definition of the thermal efficiency is equal to Q added multiplied by eta thermal. Eta thermal is equal to working it over Q added. So working it will equal to Q added multiplied by eta thermal. If I took V1 as a common, so it will be 1 minus V2 over V1, which is 1 over R. So we can make it R minus 1, and here we have R. And here we have the indicated mean effective pressure. If I divide it here by V1, so that this term is dimensionless, this term will become dimensionless also. Q added divided by V1, V1. Thermal efficiency is dimensionless. R is a dimensionless parameter also. So now we have this relation also. We can develop for Otto cycle. We have already developed for Otto cycle, for diesel cycle, and we can develop this one for a dual cycle. Then we can compare all of this cycle based on the operating compression ratio. I will give you, inshallah, today a detailed comparison between both of them. When we have the same heat added, which engine will be actually more efficient in this case? When we have the same heat rejection, which engine will be more efficient in this case? Gasoline engine, diesel engine, which is early version diesel engine, or when we are talking about the dual cycle, which are the modern gas diesel engine, which one will be more efficient in this case? So this is يعني شباب why we are developing those relation in the dimensionless form. Okay, is that clear يا شباب? Do you have a comment on that? So يعني I think you have already should have seen those cycles, the fuel air cycle somewhere before. But here يعني we are trying just to implement them for the case of gasoline and diesel. طيب, let's look at this example يا شباب here. يعني those are a kind of explanatory example. Just we will go through the cycle from the initial state up to the final state. Usually we are, what is known actually from the engines, that we can have the compression ratio should be known. The compression ratio, even in this example, he said we have a diesel engine working on a dual cycle. As the compression ratio is given, it's equal to 18. And the condition at the beginning of the compression stroke, which almost those are the intake manifold condition, intake manifold pressure and intake manifold temperature, very close to the atmospheric condition at point 1 in case of naturally aspirated engine. But in case of his turbocharged or supercharged engine, in this case the pressure at point 1 should be higher, because in case of turbocharged or supercharged, we use a compressor in order to raise the pressure of the air, in order to introduce more air to the system. So if we have turbocharged engines, the pressure at point 1 should be higher than the pressure in the intake manifold. Type here he given this problem, the pressure at point 1 at the beginning of the compression stroke is equal to 115 kilopascal. Temperature is equal to 25. يعني please يا شباب make all the temperature in Kelvin. It will be 298. And he gives the specs for air, يعني specific heat ratio K, and he gives the value of specific heat at constant pressure. P is equal to CV over CV. They give K and they give CB, then we can give the value of CV. Okay, and we have also CV minus CV is equal to R. Yani we are following the ideal gas model, so we can apply all the ideal gas relation. But he said the maximum cycle pressure and the temperature are equal to 9 megapascal and 2000 degrees Celsius. At which point, شباب, we should have the maximum cycle pressure and temperature?
3.
Is it 3 before at the middle of combustion or after the combustion? This is the BV diagram, right, شباب? So B3 is the same as B4.
4, Doctor.
It should be 4, exactly. So in this case, if I told you I have the maximum cycle pressure, so that we are talking about pressure and temperature, we are talking about the pressure and temperature after the combustion process. So the pressure B4, which is the same as B3, this is the constant pressure process, is equal to 9 megapascal, so which is 9,000. Let's make all the pressure in kilopascal and all the temperature in Kelvin before starting the solution. Usually those values will be given, CB and CV will be given in kilojoule per kilogram. So it is better to keep it in kilopascal so that we don't have a problem with them. And here he gives also the temperature T4, which is 2000 degrees Celsius, so 2273 temperature. This is the temperature for also should be in Kelvin in this case. The specs of air are given. We need to represent the cycle on the VV diagram and TS diagram. You can see the representation. We have already done this part. And we need to calculate the pressure and temperature at all points inside the cycle, throughout the cycle inside the engine, and calculate also the thermal efficiency. So as we used to do, starting from point 1 to 2 is isentropic compression. So we can apply the isentropic relation. So T2 over T1 will be V2 over V1 to the power K minus 1 over K. That should equal to V1 over V2 to the power K minus 1. V1 over V2, which is the compression ratio R, which is given to the power K minus 1. Okay? From this relation, I can get T2 and B2. We have the temperature T1, which is equal to 98, pressure B1, which is 115 kilopascal, compression ratio is given 18, and the specific heat ratio for air is given is equal to 1.4. So based on this relation, I can get the temperature T2 and I can get the pressure B2. If you calculate the temperature T2 will equal to 947 Kelvin and the pressure B2 will equal to 6,578. That should be in kilopascal in this case. So that should be the temperature T2 and the pressure B2. Right, let's move to process from 2 to 3, which is constant volume. So we have, in this case, the volume at point 3 is the same as volume at point 2. We have the pressure V3 is the same as B4. But if we apply the ideal gas relation B2, V2 over T2, V3, V3 over T3, we have the same volume. That means we can say V3 over B2 will equal to T3 over T2. We have T2, 947, and we have there B2 is equal to 6578, B3, which is B4, equal to 9,000 kilopascal. Then we can get the maximum, not the maximum, the temperature T3 in this case, which should be, if you calculate T3, it will equal to 1,296. Okay. Now we have the temperature T3, we have the pressure B3, which is the same as B4, and we have the pressure B4. So can we get the temperature T4 if we work? How we can get it? From 3 to 4, it is constant pressure. So it will be the same relation here. That will be V3 over T3 equal to V4 over T4. But we have V3 is the same as B4. So we can say T4 over T3 will equal to V4 over V3. V4 over V3 is equal to what? Is it dimensionless parameter? V4 over V3. We have defined it as what? As the cutoff ratio, RC cutoff ratio, which is the ratio between the volume after the combustion divided by the volume before the combustion. Okay, so we have the value of RC. This is RC. We have the temperature T3. Okay. Sorry, we have calculated the temperature T3. We have already the temperature T4 is given, which is 2,273, and we have calculated the temperature T3, which is equal to 1296 in this case. So we have the temperature T4. This is given, the maximum cycle temperature, which was initially given. Okay, and we have calculated T3. If you calculate this, then we can calculate the compression ratio RC. RC, if you calculate it, it will equal to 1.75 in this case. And then for the process from 4 to 5, which is isentropic expansion. So isentropic relation, we can just apply the isentropic relation. It will be T5 over T4 will equal to B5 over B4 to the power K minus 1 over K, and it is the same as V5 over V4 over V, or the reverse. Should be the reverse. Will be V4 over V5 to the power K minus 1. By V4 over V5, we can just replace it by V4 over V3 multiplied by V3 over V5 to the power K minus 1. V4 over V3, which is RC, which we have calculated, equal to 1.75. And V3 over V2 يا شباب is equal to what? V3 sorry over V5 is equal to what? So Abdulaziz, V3 over V5. This term is equal to what?
Me, doctor.
Yes. So V3 over V5. We have V4 over V3. This is the cutoff ratio. But V3 over V5 is equal to what?
V.
1 over the compression ratio. Compression ratio is V1 over V2. So V3, which is the same as V2, and the V5 is the same as V1. So it will equal to 1 over the compression ratio. So this term, يا شباب, should equal to RC divided by R to the power K minus 1. Okay. Right, here we have R is given is equal to 18, RC is 1.75, K is 1.4. We have B4 is given 9,000 kilopascal. T4 we have already calculated. It is given already 2,273, and by this we can calculate the temperature T5. Also we can calculate the pressure B5 in this case. So by this, from starting from point 27, we can just go process by process. Then we can calculate all pressure, all temperature at all points within the cycle. So شباب يعني here the cycle, as you see, it's يعني air standard cycle based on a lot of assumptions, including isentropic reversible processes, don't have any kind of losses. We have a closed system, we don't have intake or exhaust valve. So this efficiency should be a little bit يعني, just highly extrapolated actually. So this value will result in almost about efficiency about more than 60%. But usually the efficiency of an internal combustion engine, either gasoline or diesel, it does not go actually more than almost 35%. Okay. Right here, شباب, we have calculated all temperature. Then we can calculate the heat added. Heat added in this case will equal to CV multiplied by T3 minus T2 plus CB multiplied by T4 minus T3. We have CV, and we have all temperature, all of this temperature. Then we can calculate Q added. Will be calculated in kilojoule per kilogram. Like this, we can calculate the heat rejected will equal to CV multiplied by T5 minus T1. We have CV, we have calculated T5, T1 is given, then it can be calculated also in kilojoule per kilogram. And then we can calculate the work net, which is the same as Q net, should equal to Q added minus Q rejected. You can calculate this value also, will be in kilojoule per kilogram air in this case, because the working fluid is air. Right, we can calculate the thermal efficiency. It will equal to 1 minus Q rejected over Q added, or it can equal to work net divided by Q added. Anyway, yani, you can calculate this thermal efficiency. If you calculate this value, the thermal efficiency will about 0.652, or it is about 65.2%. This is the thermal efficiency. As I told you, this is actually a highly extrapolated value. 65%, we cannot have an internal combustion engine with 65%. And it is mainly because we have assumed here that we don't have any kind of heat losses. Heat losses is equal to 0. But here, شباب, we should have in any internal combustion engine, around the engine, we should have a cooling water system that absorb about 1/3 of the power. And that's why, and the efficiency take 1/3, and the third 1/3 actually is the power output. So here, that's why the efficiency here, because it does not account for the heat transfer to the cooling water and the lubricating oil, it will be almost doubled in this case. But in reality, we have to have some heat is rejected. Type they indicate mean effective pressure, the last parameter, which is the work net. We have calculated work net divided by the displacement volume, which is V1 minus V2, which is work net divided by if we took V1 as common, so it will be 1 minus R minus 1, and here we have R in this case. Okay. Then we can calculate the indicate mean effective pressure in this case. To calculate the volume V1 ya شباب, here we have R is equal to 18. We have calculated work net. Volume V1, we can apply V1 will equal to RT1. Then we can calculate V1. And then we can calculate this indicated mean effective pressure. Is it clear يا شباب? Is that clear? Is that clear يا شباب?
Yes. Yes.
طيب, let's compare, as we have developed all the relation for all cycles. So let's compare all of this cycle, including the Otto cycle, diesel cycle, and the dual cycle. And keep in mind that Otto cycle is representing the gasoline engine. Diesel cycle and dual cycle are representing the case of diesel engine. طيب, let's compare those cycles in terms of the same compression ratio and same heat addition. So heat added is the same and the same compression ratio. We have developed the thermal efficiency as function of the heat added dimensionless parameter of B1 V1. This is the relation. The heat. Let me see. So here is شباب. RC is function of this dimensionless parameter, Q added divided by B1 V1, and it is function of RB and the R. If we substitute this RC term in this thermal efficiency, then we can get thermal efficiency only function of the compression ratio and this dimensionless parameter, which is Q added divided by B1 V1. We have done this also in detail for diesel and Otto cycle. Now we can plot the thermal efficiency for all of this cycle and replot the cycle. If we have the same compression ratio and the same heat addition, same compression ratio, that means the difference V1 and V2 are the same. To get the same compression ratio, V1 over V2 is the same. So we have the same compression ratio, same difference between point 1 and point 2. But to have the same heat addition here, from 1 to 2, the cycle for Otto cycle 1, 2, 3, and ending at point number 4. For the diesel cycle, the cycle will be 1, 2, this is the compression, and then we have constant pressure heat addition. For the same heat addition process, we will reach point 3 prime. Then we will have the expansion, isentropic expansion from this point, 3 prime to 4 prime. Then we have the heat rejection, it will be from 4 prime up to 1. But the case of heat rejected in the Otto cycle, it is from 4 to 1. So the heat rejected in Otto cycle, the heat rejected here, will be less than the heat rejected in the diesel cycle. And also, if we consider the dual cycle, part of combustion took place at constant volume from 2 to 2 double prime and the other part under constant pressure to point 3 double prime, and then we have isentropic expansion. So the dual cycle will be in between. All of the performance شباب, the dual cycle will be in between diesel and Otto cycle. Here if you look at, we have the same compression ratio. We have the same heat addition. So the same heat added for the combustion process. But now look at the heat rejection. Under this condition, the heat rejected for the case of diesel cycle from 4 prime until point 1, that will be greater than the heat rejected in the dual cycle. And it should be greater than the heat rejected in, it should be less than the heat rejected in the dual cycle, and it should be less than the heat rejected in the case of diesel engine. Type, we have the thermal efficiency is equal to 1 minus Q rejected over Q added. We have the same Q added. Type, if we have the Otto cycle have the lowest value of the heat rejected, so that means this term will be the lowest in this case. So 1 minus the lowest, that means the efficiency will be the highest in this case. And that's why the efficiency of the Otto cycle will be greater than the efficiency of dual, and the efficiency of dual is greater than the efficiency of the diesel cycle in this case. Because of what? If we have the same compression ratio, that is the representation of the cycle, and the same heat added, the heat rejected in this case for the Otto cycle will be less than the heat rejected in dual cycle, and also will be less than the heat rejected in the diesel cycle. And that's why the efficiency of the Otto will be the highest in this case. And this is also شباب the representation on the TS diagram. The network in case of the Otto cycle, as we have the minimum heat rejected, the net work is the same as net heat transfer. Net heat transfer is Q added minus Q rejected. Q added is fixed for all cycles. But if we have Q rejected is minimum for Otto, that means the net heat transfer for the Otto cycle will be the maximum. And also it will be the same, it is equal to the net work. So the net work, which is the area contained, equal to the net heat transfer, which is the area contained on the TS diagram between all cycle points. In this case, the area for the Otto cycle will be greater than that area for dual, and also greater than that area for the diesel cycle. So in overall, يا شباب, based on this representation, if we have same compression ratio, same heat addition, the heat rejected in this case, if you look here, the heat rejected for the diesel cycle will be the highest, and its efficiency will be the lowest in this case. Is this point clear, يا شباب? So,
It's clear.
Khalid, is it clear? Khalid? طيب let's move to another point يا شباب, comparison point. If we have the same compression ratio and the same heat rejection, not heat addition. So the cycle, Otto cycle will be 1 to 2 and then to 3, constant volume combustion, and then we have 0.4. All cycles should have the same heat rejection. So all cycles should be following this isentropic expansion line. But to have constant pressure combustion in diesel engine, we will have the heat is added from 0.2 to 0.3, and it will be following the isentropic expansion, same isentropic expansion line, in order to reach the same 0.4, to have the same heat rejection. Okay, but in case of dual cycle, we have to compress until 0.2, then from 2 to 2 double prime, this is the heat added under constant volume, and the other part will be the heat added under constant pressure, and then it has to expand following the same isentropic line to have the same heat rejected. But if you look at this cycle يا شباب here, which cycle have the highest net work out for the same heat rejection?
It will be the Otto cycle.
Otto cycle in this case exactly have the highest. This is the area of the Otto cycle on the PV diagram is the biggest area. That means the network of the Otto cycle will be the highest in this case. Network is the same as net heat transfer. If you look at also on the TS diagram, you will find the area contained by the Otto cycle is the maximum in this case, which is 1, 2, 3 to 4. The other cycle will be less, the area will be less. That means it will result in less network out. The Otto cycle will result also in the maximum work out of the cycle, maximum work in it, and still also the efficiency of the Otto cycle will be the highest in this case. So as we conclude, يا شباب, at the same compression ratio, the gasoline engine based on the Otto cycle will result in this case in the maximum cycle pressure. It will be able to create highest cycle pressure and the highest cycle temperature in this case, and based on that it can generate the highest work out, and also it can have the highest efficiency by the condition that we have the same compression ratio. If you look here يا شباب at this relation, the efficiency of dual cycle 1 minus 1 over R to the power K minus 1. This term represents the efficiency of Otto cycle. If we added the term between the brackets here, this is the efficiency of the dual cycle. For the dual cycle, this term based on RC and RB is greater than 1. So for the same compression ratio, the Otto cycle will result in higher efficiency based on the theoretical efficiency equation. So at the same compression ratio, the Otto cycle will result in the highest efficiency in this case. So let's say, شباب, if we compare the 3 cycle based on the maximum peak pressure and the maximum peak temperature, and the same heat rejection as well. So we have the same heat rejection, so we are following the same expansion line to reach 0.4, so that we can have the same heat rejected from 4 to 1 to all cycles. So for the same peak pressure, same peak temperature in this case, as you can see here, which cycle will result also in the highest net work out?
Still the same, the Otto cycle.
Is it the Otto cycle?
Higher network, doctor.
Network.
Oh no. This case will be
Diesel cycle.
yeah, what is D? Oh, diesel. Okay, to
Yes.
diesel.
So in this case, شباب, if you look at this cycle, the area contained by the cycle on the PV diagram representing the network. In case of the Otto cycle, which is 1 to 2 Otto to 3 to 4, this is the minimum work in it. To get the same peak pressure, same maximum pressure at point 3, and same maximum temperature, and same heat rejection. So in this case, the diesel cycle will be able, in this case, to develop higher network out, and in this case, the efficiency of the diesel cycle will be the maximum in this case. And that is, Shabab, very clear, because the diesel cycle is working at higher compression ratio. It will be able to generate higher, for the same higher peak pressure, higher peak temperature, it will be working at higher compression ratio, and it will be able to generate more work in this case. So when you compare the three cycle in terms of any other parameter other than the compression ratio, in this case, the diesel cycle should result in the highest efficiency in this case. You can look at the cycle on the TS diagram. The area contained on the cycle represents the net heat transfer. Net heat transfer is the same as net work. So you can see here the Otto cycle also will result in the minimum net heat transfer in this case. Because in case of diesel engine, to generate this peak pressure and peak temperature, they will be working at higher compression ratio, and they can generate, in this case, more work out of the engine in this case. So in conclusion, Shabab, what we can learn from this, that in case of compression ignition engine, at the same compression ratio, in this case, the gasoline engine should have higher efficiency in this case. But in case of any compression ratio, in any other case, Shabab, of comparison, other than the compression ratio, it should result actually in higher efficiency for the case of diesel engine when we compare it to the gasoline engine. So the only case that we can have the efficiency of gasoline is greater than the efficiency of the diesel engine is the case when we have the same operating compression ratio. Otherwise, the engines that can typically generate high pressure and high temperature, high maximum cycle pressure and maximum cycle temperature should have the highest efficiency in this case. And the diesel engine, as it has higher compression ratio, can work at higher compression ratio, so it can generate higher peak pressure and higher peak temperature in this case, and it should result in a better performance and a greater work out of the engine. طيب, is that clear يا شباب at this stage?
Yeah, it's clear.
طيب, all of our talk, شباب, up to now is up to the moment we are talking about the air cycle, air standard cycle, which are ideal cycle in which we don't consider the intake or exhaust valve. We don't consider the combustion process, just we consider heat added and heat rejected. All processes are reversible. We don't have any kind of losses. And mainly the working fluid is air. We don't consider in this case the fuel anymore. طيب, if you look here, شباب, at this definition of the thermal efficiency, you will find here the thermal efficiency is mainly function of the specific heat ratio K, which is function almost of the properties of air, specific heat ratio of air, and only it is function of the compression ratio R. So here the thermal efficiency evaluates the engine based only on the working fluid, which is air, and also based on the compression ratio R. It does not evaluate the engine in terms of the fuel to air ratio or the other parameter, including the specific heat. Also, we have considered the specific heat as constant in this case. And if we consider, and the specific heat is mainly a function of temperature. So usually at higher temperature during the combustion, the specific heat will be changed. And the value of a specific heat constant, the parameter key also will be reduced in this case. If key is reduced, if you look here at the thermal efficiency, if the specific heat ratio is reduced, that means the thermal efficiency will be reduced, and the net work out will be reduced in this case. But let's try to modify this cycle. Try to include, instead of air, just will include air plus fuel. And in this case, the cycle will be called as the fuel-air standard cycle. Still, it is a standard cycle. We will consider the compression process and the expansion process are isentropic, and also will assume the combustion that take place instantaneously. In case of Otto cycle, it will take place instantaneously when the piston reaches the top dead center at constant volume. And also in case of diesel cycle, we'll assume it under constant pressure. So we'll assume the same standard process, isentropic compression and expansion, and the constant volume and the constant pressure process for the heat addition. But what we will add here in the fuel air cycle, the charge will be considered as a mixture of air plus fuel, not only air, so that we can see the effect of the fuel to air ratio on the thermal efficiency. Here the thermal efficiency will be not only function of the compression ratio R, it will be function also of the fuel to air ratio, because we will consider the fuel within the working fluid, which is a mixture of fuel plus air. And also شباب here, instead of heat added under constant volume and heat rejected under constant pressure, and we don't have combustion, in this cycle, in the fuel air cycle, we will consider the combustion process. So we can apply the combustion analysis for the combustion process in case of gasoline and also in case of diesel engine. Also, as we are considering the mixture will be fuel plus air, so we'll have the intake valve will be considered in this cycle, and also the exhaust valve will be considered in the analysis of this cycle. That means in the fuel air cycle, the cycle is not a closed cycle anymore. So we have considered the intake valve, we have considered the exhaust valve, so the system is an open system in this case. And also, instead of adding heat and rejecting heat, if you look here for the Otto cycle, in the air standard Otto cycle, the system is closed, and we consider instead of combustion, we just consider actually heat is added. But here in the fuel air cycle, we will consider the real combustion process in this case. But there are still some assumption. As I told you, still it is the compression process and the expansion process still they are isentropic. And also heat combustion process, we have instantaneous combustion. We assume the combustion will take place at constant volume in case of Otto cycle, will take place at constant pressure in case of diesel cycle, and it will take place at constant, part of it at constant volume and the other part at constant pressure in case of the dual cycle. But in this case, شباب, we consider the detailed combustion process, and we can apply the combustion analysis that we have learned. We can write down the combustion equation, and then we can calculate the heat transfer out of the combustion process based on the given excess air ratio or the equivalence ratio. So now in this case, شباب, you can see the fuel to air ratio will be part of the analysis of this cycle. Now we can take the effect. In this case, this effect will be reflected on the efficiency in this case. طيب, if we calculate the efficiency شباب based on this fuel air cycle, will it be less than or greater than the efficiency compared to the air standard cycle? Which one will be higher?
So probably be less than air.
So here, شباب, we are going, yes, exactly, we are going close to the reality, the real case. We are considering combustion, considering the real case of the engine. We have intake and the exhaust valve. So we are considering here some of the losses within the engine. And also we consider variable specific heat. We don't assume that the specific heat ratio K is constant before and after combustion. No, it is not constant anymore. And in this case, we will be calculating the cycle performance very close to the reality, the real case in this case. And the efficiency will be less than the limiting efficiency based on the air standard cycle. So the air standard cycle can result in the limiting efficiency in this case, or the maximum efficiency of the engine. Fuel air cycle is still, شباب, we are assume the compression and the expansion are isentropic. That means those processes are reversible. That means we don't have any losses during the compression or expansion stroke, and that does not represent also the real case. So still the efficiency calculating using the fuel air cycle is less than the actual efficiency of the engine. But it is good representation of the engine efficiency, as it take care of the combustion process and take care about the fuel, the effects of the fuel to air ratio on the thermal efficiency in this case. Okay, شباب? So in this cycle, we assume that we have intake and the exhaust valve. We have in this case the combustion process, still the isentropic compression and the expansion. But during the compression stroke, we consider the charge actually to be a mixture of fuel plus air instead of only air. And we assume that this is a frozen mixture. The unburned gases during the compression stroke, we assume those gas mixture are frozen. They are not under any kind of chemical reaction. And also we have subsequent to the combustion, once the combustion takes place, all the reactant will be converted to product. So we assume complete combustion of the fuel, and we assume that all product will be at chemical equilibrium. Chemical equilibrium, that means we don't have any reaction, forward or reverse reaction. So we'll assume that we have chemical equilibrium once we end up with the combustion process. However, يعني يا شباب, this is not the real case. So for the case of, let's say, the dual cycle at point 4, that should be the end of combustion. But actually the reacting mixture inside the cylinder, still the gases are reacting. We have still some unburned fuel. We should have also some intermediate reactions still are ongoing. So in this case, we should not be able to reach equilibrium after the combustion process. But we assume here that we have complete combustion. All gases will be reaching equilibrium after the combustion process, and it will be converted to product in this case. Here are, as I mentioned, the analysis, as we said, in case of comparison of air cycle, air standard cycle against the fuel air cycle. The air standard cycle give us efficiency only as function of the compression ratio. But here actually in case of fuel air cycle, in this case, it can take the effect of variable specific heat. Also, it can take the effect of fuel addition. So in this case, the efficiency should be function of the compression ratio and also function of the fuel to air ratio. And it will take care about the effect of variable specific heat in this case. So here, the air cycle, as we said, does not take care about the fuel to air ratio. The analysis based on the closed system and the constant specific heat. Here the system is open, we have intake and the exhaust process. Here also the analysis gives much higher efficiency, as we said, because we consider all processes are reversible. We don't have any kind of losses. The system is closed and the working fluid is air. So the efficiency will be the limiting efficiency in this case. But the case of fuel air cycle, it should give us efficiency that is close to the real case in this case. If you look at this cycle, in case of gasoline engine and the compression ignition engine, the intake process, because we have considered the intake and the exhaust valve, while the intake process, the charge to the engine will be air plus fuel. In case of gasoline engine, we should have air plus fuel, plus some residual gases that are remaining from the previous cycle. Usually, during the exhaust stroke, the engine cannot exhaust all of the gases. So part of the gases will be remaining inside the cylinder. And it will be taken actually in the next cycle, when the piston during the intake stroke. So the charge here considered in the analysis of the cycle in case of gasoline engine will be air plus fuel, plus some residual gases from the previous cycle. Also, we may have some exhaust gas recirculation. In some engine, to reduce the temperature of combustion, just we take part of the exhaust gases and return it back to the intake manifold to lower the combustion temperature. And then in this case, we can lower the emission of NOx. NOx emission are created at high temperature. So the charge to the gasoline engine will be air plus fuel, plus some residual gas from the previous cycle inside the engine itself. Plus, if we have some residual gases are recirculated into the cycle back, that should be the charge in case of the gasoline engine under the analysis of the fuel air cycle. In case of diesel engine, while the compression stroke, the charge is only air. We don't have fuel. Fuel is injected at the end of the compression stroke. So in this case, the charge will be air plus recycled gases, exhaust gases, plus some residual gases. If we have exhaust gas recirculation plus the residual gas in this case. So the difference here, شباب, between gasoline and diesel in terms of a charge during the intake stroke, the difference is that the case of diesel engine, we don't have fuel in this case. Okay, and this charge actually is compressed during the compression stroke, and at the end of the compression stroke, we should have the injection in case of injection of the fuel in case of compression ignition engine or diesel engine, or we should have a spark in case of gasoline engine. And in both cases, the combustion takes place instantaneously. It will be converted to combustion product under chemical equilibrium. Then we can have the expansion process. We should have the combustion product, including carbon dioxide, carbon monoxide, oxygen, nitrogen, All of these components should be there. But usually in the diesel engine, شباب, we should have some particulate matter, and also we should have some soot in this case. This is in addition to those combustion product in case of diesel engine. And during the exhaust stroke, we should have the combustion product, mainly should be nitrogen, carbon dioxide, and water vapor. Here also in the diesel engine, during the exhaust, it should be mainly nitrogen plus carbon dioxide plus water vapor plus some oxygen. Why in diesel engine شباب we should have some excess oxygen in the exhaust?
I think because the ignition is of ignition, so we need.
Is it related to this, or we should usually in diesel engine it works a little bit lean, so we should introduce a little bit more air in case of diesel engine. So the excess air factor lambda is greater than 1 in case of diesel engine, and in case of gasoline engine usually it works stoichiometry, very close to the stoichiometry. So in case of diesel, as the combustion takes time, we need more air in this case to be supplied to the engine. So in this case, that's why we should have some excess oxygen in the case of diesel engine. Okay. So is that clear, Shabab, the difference between the fuel air cycle? I will start introducing the cycle on the PV diagram and look at the different processes. I will not go in deep in the analysis of this cycle. Because in this cycle we have to get the properties at each point, but we are not following the constant specific heat analysis. So in this case we have to follow the table and the chart. This you can practice it somewhere. You can try it in the book by G.B. Hewitt. There are different table and the chart based on which we can calculate the values of the properties, the internal energy, and also the enthalpy at the different point inside the cycle, and then we can calculate the thermal efficiency. Just what we are doing here, what we are going to do here is just will be representing the actual cycle in case of the fuel air cycle, the cycle processes, and I will give you indication about the thermal efficiency in this case as function of the fuel to air ratio. But the detailed process and the solution of the cycle and the cycle analysis, that will not be a part